Okay, so today practical is going to be about association and sequential analysis. Okay, that's a practical 9, not 8. Anyway, so if you have already done any revision, so what was association rules for? Association rules. If we take market basket analysis as an example, where we are looking to extract interesting relationship between items, right? Between the occurrences of items inside the data set. For example, taking transaction data set. So we can come up to rules such than those, right? Like these rules where we have diaper, for example, lead to fish. So remember how to read these. Simply, we are looking into saying that if the customer has placed diaper in his cart, then there's a chance of placing or taking fish as well. Okay. So in this example, by the way, in order to run this code, you need the data set inside the GitHub. So go back to the GitHub. There's a file inside Practical 9 folder, grocery store data set. You know how to download? If not, then click first on CSV file, and then there's here 3 dots button. 3-dot button, you click and then choose download. Then the file is going to be on our local machine. We need to upload this file to Colab. To Colab environment, then you go here to the files, click, then make sure you initialize the engine. Then you right click, choose upload. Then navigate to the location where you have downloaded the grocery file into your local machine, select the file and upload. Okay, so you should have the file listed under the Files tab section. Okay, for this example, we are going to use ML extend for association rules. So inside Colab, it's already installed, so you don't need to install ML extend on your Colab environment. But if you are working on your local machine at home, so make sure you install this package first, right? So you know how to install, correct? You are expert now, pip, install, and then ML extend. Anyway, for Colab, no need. But once you go back home, then you may need to install the package first before running this practical. So we are going to use from ML extend under frequent pattern module 2 functions, a priori and association rules. So you can run this section and then load the data set to ensure that the data set has been uploaded correctly and you are able to retrieve the file. Now, if you look back to association rule mining, before we start working on doing any item set generation or association rule generation, we need to ensure that we do proper preparation for our data set. We need the data set to be binary, have binary representation. So for example, taking this data set, we need to convert it to such way where the items are the columns. And then for each transaction, the items that belong to each transaction, we need to mark by the value of 1. 0 means no values. So taking the first transaction has only 2 items. So we mark bread and milk as 1, the rest as 0. Okay. So in order to do this, we are going to use transaction encoder from ML extend. But before doing that, if we look back to the transaction data set, each transaction has a bunch of items. Those items are identified or separated by a comma. Right? There's a comma to split between the products. So we are going to split the items by calling the split function and using comma as the separator in order to split our items into separate products. So at the end, you're going to have a list for each transaction where the items are clearly listed inside. So for example, taking milk, bread, biscuit, for this one, we have 3 items. The first one, and now they are been splitted up properly and inserted into a list. Now the second step you need to do, now you can use transaction encoder. So we define an object, then we call fit and transform, same as usual. And finally, we place the data inside data frame for better presentation. So you can see the data as well as the column. Right, so now you can see we got binary representation of 1 and 0. Okay, true means 1, false means 0. Okay, so again, taking the first list, we had milk, bread, and biscuit. So we can see that we got bread, biscuit, true, bread, true, and milk, true. The rest are false because they are not part of the first transaction. Okay, so far? Now, how we can generate association rules. So looking back into the slides, we have two main approach. The first one, you need to generate frequent item set. Okay, not any item set, but frequent item set. So we use the function a priori, so we are applying a priori principle. So we already explained. We explained last week about brute force approach and a priori principle. So now we are using a priori. So we pass the data that we have prepared, right? That we have pre-processed and binary representation. And then we need to provide the minimum support. Because remember, in order to call an item set a frequent, that this item set has to have a support which is greater or equal to the minimum support. So now we need to define the minimum support in order to differentiate those normal item sets from the frequent item sets. So here we have decided to go with minimum support 0.2. Once you call this function, you're going to have the frequent item sets passed back to you. So here you can check. We got, I think I didn't call this one, I already called. Okay, so you get all of these item sets are frequent. So we got one, we have frequent 1 item set and also frequent 2 item set. So here just showing the first 10. If you print out the full list, then you have also frequent 2 item set. And notice all the support for all the item sets fulfill the condition where the support is equal or greater to 0.2, the one that we specified under the minimum support argument. So now we got the frequent item set. What is the second step we need to do? We need now to generate the rules. So we call association rules function, and then we provide the frequent item sets, right? Because only we generate rules from frequent item sets. And then we need to provide the metric. Remember, also association rules have metric to evaluate. So we have chosen confidence. And then for the confidence, we are looking for the minimum threshold 0.6. Okay, that means the minimum confidence threshold is 0.6. Because remember, we are going to generate which rules? The rules that have high confidence. So we're looking for high confidence. So we have specified the confidence here, 0.6. That means all the generated rules must have confidence equal or greater to 0.6 or 60%, in other words. So here we got 5 association rules generated from frequent item set. Now how to read these? You have 2 columns, antecedent and consequent. Antecedent referring to the item set before the arrow. So X leads to Y. So these, for example, this item set milk and diaper is called antecedent. The item set after the arrow called consequent. Okay. So back here, that means milk lead to bread. And what is the confidence? 0.8, 80%. We are confident 80% that if the user pick or take milk, there's high chance of 80% of taking bread as well. Okay, and same for the rest. Sugar leads to bread, and cornflakes leads to coffee, and so on and so forth. And you have the confidence here. Notice all the confidence for all rules fulfill the minimum threshold, where the confidence equal or greater 0.6. So now you have the rules at your hand. What you can do? What can you do with them? Throw them in rubbish. All right. So what can you do? Back. What are the benefits we discussed about association rules? Yeah, so for example, you can have shelf design or for your store. So you have many products and you don't know which products you can place next to each other or near to each other. Then those rules is going to tell you. That means try to place the bread near to the milk. So don't put it too far, if you like that way. Or you may do cross promotion, right? You can apply cross promotion. Where was it? Yeah, so you are able to read the purchasing habit, not mentioned here, but you can do cross promotion. So for example, if you like to increase the sales, probably you can pick those rules saying if the user purchased sugar along with bread, then you can give him some promotion to increase the sales. Okay, any other question? Oh, so far no question, just I'm asking any other one. Not sure if anybody posed question. Oh, no question. Okay, no question, then we're gonna move into the next topic, which is sequential analysis. Now, sequential analysis we haven't discussed yet, but it's good now you are exposed into the topic before we carry on during the lecture time. So what is sequential analysis? So looking back so far, we were looking to association rules, and we took an example, market basket analysis. So in market basket analysis, simply we have a bunch of transactions, and we are interested to find relationship between the items, the occurrences of these items together, right? Or one item leads to another. So for example, in market basket analysis, we had only the transaction ID and item set, but now we are looking into sequential analysis. So again, in market basket analysis, we were looking to associations, interesting relationship between items, right? So we can describe what is, for example, if the occurrence of such item happens, then what is the occurrence of carrying on for another item? What is the occurrence or co-occurrence, in other words, the co-occurrence for another item set? But in sequential analysis, we are more interested to look to the data in a different way. Let's say that if you look into this example where you have customer ID, we have recorded. So earlier in market basket analysis, we didn't care about the customer ID, right? Only we cared about the transactions. Now, let's say we managed or we recorded also took into account the customer ID. So for example, here we can see that customer ID 1 has made 3 transactions in the store. So for example, at one occasion, earlier occasion, so transaction ID also, by the way, referred to the sequence of transaction, right? So that means the first transaction happened by this customer where he or she has purchased A, B, and D. Then following transaction, maybe after 1 day, he came back to the store and purchased B, C, and D. And later, at some time later, he came back and purchased B, C, and D. Now, in sequential analysis, we are interested to know what is next. So now we know that this customer has done these purchases, but now we are interested to know what next, what this customer may purchase in the future. So we are looking into the sequence. So we know now the first item set happened this one, followed by this one, followed by this one, and now we are interested to look what's going to be in the future, right? So actually can be interesting, you know, like you can send, sometimes you can send emails giving the customer, you know that, for example, the customer is interested to purchase this, for example. Then you maybe send them email giving him promotion to encourage him to do the purchase, right? Because you know that there's a chance the customer is interested in this product. So this is in short sequential analysis. So in comparison to market basket analysis. Any question? No question. No question. Now we are going to look into special case of sequential analysis, which is time series. So we're not going to spend time on market basket analysis using sequential analysis, but we are looking into special case of sequential analysis is time series. If anybody interested in this topic, so today we are going to discuss and later during the session as well. So what is time series first? Time series refers to a sequence of data points collected or recorded at regular time interval. For example, you are recording the temperature every 1 day, right? So here, what does it mean? You have recorded collected data points at regular time interval. That means every day you are collecting one temperature value. Okay, so you have equally spaced over time where you collect your data. For example, if you look here, we have some figures. So the first figure is showing you, by the way, for time series, there are two types. You have univariate time series, and you have multivariate time series. Same, by the way, regression. Regression also has univariate regression and multivariate regression. So all the time, we were discussing about univariate regression all the time for this course. But it's good to know there's also multivariate regression. Multivariate regression, simply you are looking to predict two values using the same model. So you have y1, y2. Both of them are continuous value, and you are using regression analysis in order to predict these two values at one time. But like your case in your assignment, you were doing univariate. So you were looking only to predict the travel fee. So it was univariate regression. Same in time series, we have univariate and multivariate. Univariate means you are collecting one data point at a time. For example, every one day you are collecting the temperature. So how many values you are collecting at every time? One value, which is the temperature. So this is, we call it univariate. Multivariate, simply you are collecting more than one data, one value at a time. For example, maybe you are collecting the temperature and humidity and so on, right? So you have more than one value collected at a time. This is, we call it multivariate time series. Clear? So multivariate time series can be useful, for example, taking this interesting figure. This showing us the visitors, the number of visitors per month, along with the changes of temperature, are recorded in one figure. Now, what we can see here, that as the temperature increases, the number of visitors increases as well, right? So this can be interesting, showing there's a relationship between visitors per month and temperature. And that can be logical. During summertime, right, people or usually schools are off, especially like if you go to the four-season country. So during summertime, no school, it's hot. And then students just have off from school, and that means the vacation time starts, right? So that's why that will answer the question why we have high number of visitors when the temperature is high. And same, the number of visitors will drop down when the temperatures goes down as well. Time series can also be used to do data imputation. So you already knew what is imputation, right? Where we calculate some value and then to replace with missing value. So for example, you look into this figure where you have a blue line, but we have some missing value. We have interruption of the data, the collected data. Then you can also use time series to impute, to calculate the missing value for those, the one that in red, okay? Also can be used to do anomaly detection. So when you draw a figure, you can easily spot, for example, here there's a hike or spike in the value for some value, right, at this time. And this can be marked as anomaly. Anomaly is another word for outlier. So also anomaly detection can be called outlier detection. So in this case, we know that there's something happened here, which make, for example, the value for some variable goes out significantly or goes up significantly, deviating from the normal values. Okay, any question? So looking back here, for this example, we are going to use dummy data. So in order to create this dummy data, just run the following code. If you don't want to understand, that's fine. This is only for the purpose of creating some synthetic data or dummy data for this exercise. Okay, so you see that we have generated this data. This is synthetic time series, and obviously you can see it's univariate, right? We have only single line showing in this figure. If you have more than one line showing the changes for different values, then becomes multivariate. Now, what we can observe from this figure, do you see anything from this figure? Anybody has knowledge in time series, maybe working in stock prices, buying, selling, gold, Maybe doing business. Anybody works with gold? Nobody? Okay, never mind. Okay, now we have univariate analysis first, but what we can sense or interpret from this figure. Now, for time series, there are some characteristics we can describe time series figures. Let's look into that. The first one is trend. What is trend? Trend simply where you are looking for relationship or underlying pattern, growth or decline in time series data over a long period of time. For example, if you take this figure, you see that, let's say this value is about prices or sales of items over time. Okay, so let's say that this value represents sales of items over time, the total sales of items. Now, what we can see over the time, that the total number of sales increasing, right, over the time, like the one we saw earlier, or no need to look into that one. Anyway, here you see that there's upward line, meaning that you have increasing, right? You have growth, in other words, for the total sales. So this is, we call it, in this figure, there's a trend. The trend can be upward or maybe can be downward. Maybe the total number of sales drop down over the time. So we say there's a trend, but that trend is drop down. Now for this example is upward. Now when we say that there is no trend, when can we say that we have no trend? When? Yeah, so if it's going up means we have upward trend. Going down meaning downward trend. Then when we say there's no trend. Yeah, very good. So when we have horizontal line, if you draw horizontal line, then that means we have no trend. For example, if you look to the oil price, let's say for 95, because one of your friends said 97 is not controlled. The prices, the oil price for 97 keep changing. So if we take the 95 and we collect history data up to 1 year before, and we draw a figure, what the figure or the line is going to be? It's going to be horizontal. Why? Because looking since 1 year at least up to today, the price is fixed, right? No changes. It's always 2 ringgit and 5 cents. So that means if you draw a figure presenting, let's say 2.2 ringgit, then the line is going to be over the time horizontal because the price is controlled by the government. It's not changing. So in that sense, we say the oil price for 95 has no trend because there's no upward trend, no downward. I mean, the price is just fixed. Now, looking into this figure, do you see there's a trend or no trend? Yeah, so there's a trend, right? So there's a trend, meaning how you can understand, if I ask you to draw one line to present all these data, make it just straight line, like linear regression, then the line is going to be pretty much somehow similar to this, right? Meaning we have a trend. So this data, the one that we have created, has a trend. What else? Now, the second characteristic is seasonality. What is seasonality? Seasonality refers to the regular or predictable fluctuation that recur over a specific period of time. For example, looking into this figure, don't you see there's a repetitive pattern happens over a time? For example, looking here, starting from 0, and then we went up to 1, then down to -1, then back here to 0, right? And then same pattern is being repeated again and again and again. So this is, we call it seasonality. That means this figure showing us an example of seasonality where you have repetitive pattern showing over the time, getting repeated over the time. You can think of it of seasonality like, for example, how ice cream sales goes up during summertime and drop down during winter. So for example, if you go to my country, we have winter. So actually, if you look for the sales for the shops during winter time, you won't see that they are selling ice cream. And even if you ask them, they might think you, oh, what's happened? People usually don't request for ice cream during winter time. Imagine the temperature is 0 degrees, people are freezing, and then you are looking for ice cream. So the point is, we can say in this case, in this example for ice cream, we have seasonality, where the sales for ice cream goes up during summertime and drops down during wintertime. Now, looking back here, do you see there's seasonality or no seasonality? There's seasonality, right? So if you notice, there's a repetitive pattern, same over the time, keep repeating, right? So now we can sense from this figure there's a trend and seasonality. So actually a figure can have both, can have trend and seasonality, like this example, same. Okay. Now another characteristic is autocorrelation. What is autocorrelation? Autocorrelation is the relationship between a value at specific time and its preceding or succeeding value. For example, if you take this example into consideration, if you sleep well, if you have slept well, for example, for the past few nights, so what is the chance that you're going to sleep today well as well? It's going to be a good chance, right? So that means we can say that there's autocorrelation between the past values and today value. So if you last few nights you were sleeping well, then there's a good chance today you're going to sleep well as well, right? So this is what we mean by autocorrelation, where such value at specific time, like this one, okay, has connection or relationship between it and its preceding or succeeding value. Again, take another real example. If we are talking about gold price, let's say today gold price is 5 ringgit, for example, for 1 gram. Now, what is the value is going to be tomorrow? Somehow near to 5, either maybe slightly higher than 5 or lower than 5, right? So there's a relationship between the value and its preceding one. So that's why here correlation simply where you're taking the value for today, let's say at time t, and the value of time t minus 1, let's say it's yesterday, by multiplying by some ratio, which is going to make it going up or going down. By the way, there's no noise here. This is wrong. I'm going to fix, hopefully later, if I don't forget. In this figure, there is no noise. There's no noise. But in reality, you will have noise. So again, this is the figure without noise. Now, if you add little noise, the figure is going to look like this, but still have autocorrelation. The point is always going to have noise. So you won't see the figure like this, smooth, very clear looking, where the values are connected to each other, right? So always you're going to have some noise inside your data set, and the data will look like this. But the point is still same. The value at some specific time, it's related to its preceding or succeeding value, okay? And the equation is still here. So we still have autocorrelation anyway, but just we added some noise into the figure. Okay, so in reality, this is more realistic than this one. So same here, we have also autocorrelation where any value at specific time has relationship with its preceding or succeeding value. Okay. Any question? Now the last characteristic, okay, noise, we know that always that noise is simply some random variation inside the data that doesn't contain any useful information. Okay. So noises can come because of different sources, but noise will exist inside the data anyway. Now the last one is stationary or non-stationary data. So usually when we work on time series, data set should be stationary. What do we mean by non-stationary or stationary data? So a time series is said to be non-stationary if its statistical properties like mean and variance change over time. For example, if you look to this one, this is an example of figure for stationary, right? So you notice that the mean or the variation for the values going up and down is same. But if you take this one, the non-stationary, where you have changes in the mean. So if you take this bunch of data, you see that the mean is quite different than the other part of the data. So you have sudden change in the mean, right, of the data presented here, or maybe the variance. So you notice the variance here were lower and suddenly became higher. So this is, we call it non-stationary data. This is stationary data. So our example here, of course, this is stationary data. We don't see like there's something out of the rhythm suddenly happen, right? We don't have these kind of changes. But most of time series model assume the data is stationary, and you often need to transform non-stationary data to make it stationary before you can effectively develop a model for it. Okay, any questions? So now we understand when we look into this figure that it has a trend, it has seasonality, autocorrelated, and stationary data. Okay? Of course, also with noise. You see the noise? These where you have little variation going up and down. These you can call them the noise inside your data. Any question? Clear? So now you are interested with time series? Not yet. Not yet. Maybe next year. Or maybe the year after. Okay, when we work on data set, right, usually we need to split our data into training and validation. But how to split the data? Is it similar like the concept we studied so far when we conducted, let's say, a regression or classification? The answer is no. You still need training, validation, and test set. But the way that you split your data is you need to be cautious. When you split your data, of course, you're going to have training phase or training data set, validation data set, and test data set. But how you can split up your data? It's important to make sure that each phase of these phases encompasses a complete set of seasonal cycle. Okay, what does that mean? So if we take back, this is our figure for the data, right? So if we draw it or take a snapshot, start making surgeries. Now, this data set, as I said, it's dummy data, is synthetic data. And if you look back to the code, actually this data has season. And this season happens or repetitive every 365 days. So that means we have yearly seasonality. So you need to measure also your seasonality. Maybe every 6 months you have repetitive pattern, maybe every 1 year. Okay, so you need to look. For this data, it's repetitive every 1 year. So if we look back here, so started from 0 to 1 year. 1 year, that means 365. So let's say it's going to be somewhere here, 365. Drawing. Then after another 1 year, so 365 by 2, 365 by 2 should be 700, what? By 2, 730. Right, so if we take 700, should be in the middle, a bit more, 30. Okay, so you notice the seasonality happens every 1 year. I should have chosen this easier. Right? So now the point is when you come to pick your data for training, for example, you need to ensure that the data has complete set of cycle. So that means, can we take this data to become our training? Cannot, because this one has 1 season and a half, let's say, right? 1 year and a half, and the season is complete 1 year. So either can be here, okay, if you like to take it like this is okay, but the point is you need to cover complete season cycle. Here also okay, right? And so on. So we have 4 years here. The data set has repetitive pattern over 4 years. Is it clear? So then maybe you would take this as your training data set, and the remaining part goes for your, let's say, validation set. Or you can have part for training, validation, and test. So for this example only, I'm going to show you, we're going to talk about training and validation, but same way for test set. Okay, now validation set usually is the recent one. So don't take validation the early year, because validation set should be, when you validate your model, should be more resembling the recent values for the current year or the last year. So validation set usually is the last portion of your data, or the recent data. In other words, the recent data. The earlier data can be used for training. Is it clear? So this is why here you need to ensure that you have, again, complete set of cycle, seasonal cycle for your data. Okay. Okay, and this is fixed partitioning, by the way. There are two types, roll forward partitioning. I'm not going to discuss, but here this is fixed partitioning, where just you fix your partition from beginning. Roll one, yeah, that you mean keep going in rolling or rolling, including more data at every phase or at every time. Now for evaluation, you can use the metrics for regression. So you have mean square error, root mean square error, and mean absolute error, and so on. Okay? Let's split our data. So for this example, we're going to split our data. Again, the data has repetitive pattern over 4 years. You can check here. We multiply 365, right, by 4. So we are taking for 4 years data. So I have splitted my data into 1095. So I assume just I took 365 multiplied by 3, then it's going to be 1095. So I put 1095, or even some people put 1100, also can. So we split our data. Now, if you look into the figure, what we have, two info. We have time and value. All the time, remember, we have time and we have value, because sequential data is very essential component to have the time. If you capture, let's say, temperature, you keep capturing temperatures, but you don't know which this value belongs to which day. So you have no time, access, right? Then you cannot conduct sequential. You cannot do time series because the word time is already inside time series. So you need to have time while you are recording your information. So here we split our time for the training data and the time for validation, and same for the data, the actual data for training and validation. So if you draw the training data, this is going to be your training data. You have 3 seasons completed, and then 1 season for the validation set. Okay? Any questions so far? No question. Okay, now we need to look into naive forecasting. Now we need to start to look into forecasting methods. The first one is naive. Why naive? Because actually it is dummy way of forecasting. Now, if you remember back practical 6, we looked into dummy classifier, right? You remember we used dummy classifier back then in practical 6. Why did we use dummy classifier, or how dummy classifier can be useful for? Back then, we proved that accuracy won't be a good choice all the time, right, for classification. But dummy classifier can also be good for what? If you like to set up the minimum threshold for accuracy. Accuracy is a value between 0 and 100, or 0 and 1. So if you ask yourself, okay, what is the minimum accuracy that our model is supposed to have, right? Because accuracy, again, has value between 0 and 1. It can be 0.5, 0.6, being 60% accuracy, 70%, 75. But what is the minimum accuracy your model is supposed to have or to show? Then you can use dummy classifier. Like the last example, when we use practical 6, dummy classifier accuracy where? 90%. That means whatever data mining model you are building, which is the smart one, that one is the dummy, that means you should get higher accuracy than the dummy classifier. If you get, in this case, back to the practical 6 where we had dummy accuracy using dummy classifier 90%, if your model showing accuracy 80%, is it acceptable? No, because that means your model is dummier than the dummy classifier itself, right? I mean, dummy classifier can do better than your model. So again, dummy classifier back then, we can use it as minimum threshold. By the way, for regression also, there is dummy regressor you can use inside scikit-learn. Now, similarly, in time series, we need to do some such approach. So we come into naive forecasting. So hopefully now you understood the following step, why we are doing. But what is naive forecasting at the first place? Naive forecasting is very simple. And actually, it is naive way, as the word indicates. In naive forecasting, we take simply the last value and assume the next value will be the same. For example, if I ask you, what is the gold price going to be tomorrow? Okay, not ask you. Let's say if we ask the naive way. So naive says, okay, what is the price for gold today? Let's say it's 10 ringgit. then it's going to assume tomorrow is going to be 10 ringgit. So there's no smart anything in there. Even there's no calculation. Just whatever the current value, you assume this is the same value going to be for future. Okay? So this is naive forecasting. Now, if you apply naive forecasting, as you notice, it's only this line, where only we assume the forecasted value is going to be the previous value. This is why we took split time, because we're looking only for validation set. Because we are interested only in the validation set. This is why we took split time again. But the point is we took -1. We are shifting. We are shifting. That means the forecasted value for today is yesterday. And the value of yesterday is the day before. And the value of last 2 days is the value of last 3 days. And so on and so forth. Okay? This is why we are shifting the value one way back. So that we use it to forecast. We assume this is going to be the forecasted value for next. So what does that mean? If you take example, let's say if you like to check on the time, the value at the time 100, let's say 100 seconds, 100 days, it doesn't matter, time step 100. Then if you look to the validation set at 100, it's going to be 55.9. So naive forecasting will assume the next value, you see, is going to be 55.9. You got it? So this is what we mean by naive forecasting. Now, if you draw naive forecasting, it's going to look like this. So you see there are 2 figures here. By the way, I have plotted 2 figures. The first one, the blue one, is validation set. And the orange one is for the forecasted value. If you zoom in, you see, now you can see clearly that there are 2 figures, blue and orange, right? And you say actually it's doing good. But again, this is naive forecasting. There's nothing, just assuming the current value or the value at some time is the value of the previous one. Okay? I'm talking about the forecasted, the orange one. So this is why you see that the peak, there's a shift by 1 unit. So whatever the value at the blue at time t is going to be the value, the forecasted value for t plus 1, and so on and so forth. Now, after we prepared the forecasted value, then we can use mean square error or mean absolute error. So for example, let's look into mean absolute error. So we see that we got 6.08, right? So now we can use this value as a threshold to evaluate our smart models. Let's say the following models that we are going to use. This is the naive one, right? Now, since this is the mean absolute error, let's say the subsequent model, whatever model we are using, should it be better or worse than this value? Better. Better means? Yeah, should be less than 6.08, right? So this is the naive forecasting. We can fix it as benchmark. Now, the following values, whatever models you are doing, supposed to get lower than this value, because this is error. Now, by the way, guys, always I'm telling you, don't memorize. If lower or higher, just look. This is the value for what? This is the value for error. If you ask primary school student, right, when you tell them error should be less. You do less error, better. So that means lesser, the better. So you don't need to memorize. I told you, if you just try to understand, actually there's a way to avoid memorization. So you don't need to do memorization. But if we are looking for accuracy, the higher, the better. Because accuracy, when we go from 80 better or 90% is better. So higher, the better. But for error terms, the lower, the better. Okay, now we move into the one of the simple statistical approach for forecasting called moving average. Okay, so what is moving average? Moving average is straightforward prediction technique. It's very simple forecasting, where simply what you do in order to calculate or forecast. Now remember, in naive forecasting, what we do, in order to forecast the following value, we take the current value. We assume the current value is going to be the forecasted value for next. Now, in moving average is different. We don't take one value. We take a bunch of values over time frame. So if you notice, we calculate or we take a bunch of values over specific time frame, and then we calculate the average. So let's say we are taking the gold price. We try to forecast what is the gold price going to be tomorrow. So we may assume, okay, we are looking for time frame of 30 days. In this case, we go and collect the gold price for the last 30 days, and then we take the average value for these 30 days, and we assume that this average value is going to be the forecasted value for tomorrow. Is it clear? This is moving average. So a bit more smarter, or a bit more, there's now some calculation. Earlier, naive forecasting, there's no calculation. Just we take whatever, we put it for next. Now we have some way of doing calculation. This is why this is very simple forecasting anyway. Okay. So let's apply here. The function has been built to provide the data and the window size, because remember, we need time frame. So we need time frame. So we define window size, which is the time frame. And then we calculate, we take the mean for a specific period of time, and we add it inside the list. And finally, we convert it to NumPy array and pass it back. Okay, so this function is going to help us to calculate the moving average, not only for one value, but for a series of values over a specific period of time. So if we define window size 30, and then we can apply moving average forecast for our data. And then again, we are only interested with the validation set. So this step is for validation, because earlier we were calculating the moving average for all data set. You see, we took series. This is for all data. Here, just to take only the part that is related to the validation set. Now, if you draw the validation set again with the moving average, so what you can notice, you're going to get smooth line, the orange one, right? Which looks nice and smooth. Why? Because we have took away the noises, the randomness inside the data. Instead, we got smooth line. Okay, so it eliminates a lot, takes away all the noises, and gives us, or a lot of noises, not all, but gives us a curve roughly emulating the original value. But moving average has a problem. Cannot anticipate or cannot work with the trend and seasonality, right? Our data set has a trend and seasonality, right? Has a trend and seasonality. Moving average doesn't work well when data have trend and seasonality. So how to do with this? What is the solution? Is to to apply some pre-processing to take out the trend and seasonality from our data set. How to do this? We apply the concept called differencing. So what is differencing? Differencing is a mechanism to help you to remove trend and seasonality from the time series. Okay. Now, how it works? Simply, you take the difference between the value at time t and value at earlier period of time, and you subtract from each other. So you take the difference between value at time t and the value at earlier period of time. So if you look to the example here, simply we take the values at time t and then subtract by a value at earlier time. But which value? Since we have seasonality of 1 year in this example, so we deduct or subtract from the value, the corresponding value at the earlier year. So for example, if we are looking for gold price, so we have collected data for gold price 2022 and 2021, years of 2022 to year 2021, and assuming that the seasonality for the gold price happening every year. There's seasonality, repetitive pattern over 1 year. Then what we can do, we take the gold price at first, let's say 1st of January 2022, right? And then we take minus the value of gold price at 1st of January 2021. Okay, so you got the point why I'm subtracting here 365. I'm taking the value at earlier than before 365 days. That means before 1 year. So whatever the value we are looking for, we are taking, and then we subtracted by the value 1 year earlier. If you still don't understand, let's take this example. Again, let's take this. Okay, now remember that we have seasonality 1 year, right? So again, as we draw earlier, we had here, let's say 365. I've used this. Okay. And same for second, third, and the last one. Now what I do, I need to subtract each value from its preceding value at the earlier year. So I'm gonna take, I wanted to see where's the third part. So okay, this is, I think, enough for now. By 3, what is by 3? We already calculated, right? Yeah. So it's 1,000, about 1,100, somewhere here, let's say. Just for simplicity, I'm gonna push more. And then what we do the following. This is exactly what we are doing inside the code. I'm going to show you, or we are applying differencing, in other words. But let me take the time axis as well. And then we need to subtract these values from the earlier years. So we shift 1 year back, and we don't take the last year, because the last year is going to be subtracted. It's already inside the figure. We need to be subtracted from earlier one. I hope that you already have got the idea what I'm doing. Okay. Now, if we take data points, so now we need to apply differencing. That means we need to subtract whatever values here from these values. So if you like also to mimic, to show you sample, let's take green this time. So we need to subtract this value from the earlier value, sorry, this value from the earlier, right? We took, yeah, this should be on the left, and this is down. But anyway, we are doing subtraction. That means we are taking the value up here minus the value down here. Let me just take samples first. And so on and so forth. Okay, you got it? What's happening? Is it clear? So we're taking this value minus the value of earlier year. So the value here was at 3, let's say the following year. This was the earlier year. So we take each time value and subtract it from the earlier year, the corresponding value of the earlier year, and so on and so forth. If you do this, you're going to get what? You're going to lead to what? You're going to get? This is going to give you this figure. This one. Okay, understood now? What's happening? So if you do this, this technique called differencing. This is, we call it differencing. Can you see the font? Okay, so this technique called differencing. Now, what do you see again? What differencing is helpful for? To remove trend and seasonality. Now look to this figure. Do you see any trend? No more. Trend has gone away. Any seasonality? No more. Can you identify repetitive pattern? Cannot. So we have neither trend nor seasonality. And this is why we apply differencing, because again, moving average is not good when your data has trend and seasonality. So we had to take them away. So this is what we have done here in this code. The picture here I showed you is exactly to this line. Exactly this line of code. This is the same exact picture. If you like visualization, this is visualization for this piece of code. People are talking, that means they understand. Okay, so again, this picture showing you the code for this one. Any question? Okay, we're not done yet. Now we have just done the differencing. Now we reapply back the moving average. But notice on the difference data, on this one. Now we are applying moving average on this data, no more on the original data. Okay? On this data, because we removed away trend and seasonality, then we apply moving average. Then we can plot again for the validation set. So this is the difference data. And the orange one is the moving average, the forecasted value using moving average approach. But this is not the original value, right? This is the difference value. How to get back the difference value? So we have already applied differencing on the original data, and then we applied moving average on the difference data. Oh, guys, I hear many people talking. So we apply moving average on the difference data, but we are interested in the original data. Then what we do, we take this moving average that we have, and we add back the value that we took away earlier. So this is the differencing moving average, the one in orange, and then we add back the value that we took away earlier. If you do so, you're going to get this figure, which looks much better than the earlier one, this one, right? This one or this one? Absolutely this one, much better. And if you calculate now the mean absolute error, you're going to get 5.90, which is slightly better than naive forecasting. So now we are getting into something. Earlier, we got very bad mean absolute error, was 7.98, right? And then we applied differencing and moving average back. Then we got better mean absolute error, which is slightly better than the naive. Naive was 6.0, right? 8. Now it's 5.9. But why we didn't get much better result? It's only just slightly better. Because when we added back the original data, we added the noises as well, right? We added the noise back into the forecasted value. So what to do in this case? Instead of taking the original value straight away, we apply moving average on the original data. Okay, why? Because moving average will make smooth line, less noise. So we will apply moving average on the original data, and then we will add it back to the difference moving average. So this is what we have done here. So we took moving average on the original data, then we added back to the difference moving average. If you do this, you're going to get much better result. You see here, we eliminated many noises from the orange line, and then the mean absolute error, you see what's happened, has dropped down to 4.63, way much better than the earlier one. The earlier one was 5.9. Now we managed to drop it down to 4.63. Okay, clear? So moving average has helped us to eliminate noises from the data by giving us a smooth line. So the earlier data was very fluctuated, going up and down, indicating that this is the noise. So when we apply the moving average, we are getting more smoother line by eliminating the noises. So we have done this before we add back the values on the moving average, and then we managed to get much better model forecasting using moving average approach, where the mean absolute error dropped down to 4.63. Clear? Interesting, right? No. Okay.
Done the average twice.
Twice? Yeah, we have done twice, correct. So firstly, we done differencing on the original data, then we apply moving average. Then we need to get back the original data. But before we add back the original data, we apply moving average as well. So moving average has done twice, one on the difference data and one time on the original data. Yeah, so this is what we have done. Any question? So now if you like to do forecasting, then you can use moving average. Maybe you collect some data and then follow the same approach, moving average approach, which is the simple statistical approach in order to forecast for future. Maybe you are interested to forecast for tomorrow, then you can apply this. Then how you can forecast for the day after tomorrow? After you forecast the day of tomorrow, then you add it and then you take it into consideration for the day after tomorrow, and so on and so forth. Any question? Again, this is one of the simple approach. This is one of the simple approach for forecasting. If you like more complex one, you can go to deep learning. I'm not going to cover in this course. If you are interested in deep learning, then you will need to look for it in order to apply time series forecasting using deep learning, which is more complex model, should give you much better result than moving average. Any question? Yeah, this is for validation part. Then if you split your data from beginning on the training set and validation, then you can use training and validation all the time and keep tweaking your model until you have a good model. Once you finish, you are satisfied with the results, then you can use the test set to evaluate your model. So again, test set for evaluation. Yeah, same. So here maybe going back to your original data. So here we have generated data for 4 years. Maybe you take 2 years for training, 1 year for validation, another 1 year for test.
Here we got 2 years for training and
yes, for validation. Maybe we make training only 2 years, 1 year for validation, 1 year for test. Or maybe if you have original data, I mean, this is synthetic data again, or just here, come and generate more, by the way. Just make this 5, so you have more data. But again, this is synthetic data. If you like to work on real data, then find time series data set available on the net and apply the same approach, same code. Any question? Let's see. No question. Anyone like to ask the same question? Any question? Sure, huh? No question. If you like to ask same question, go ahead. If not, then I can conclude the session.